Assalamu alaikum. We're starting day 9. We're going to be practicing what we've learned in the past 2 days for the verbal section. We're practicing analogies and doing something brand new for the quantitative section. Exponents, powers, indices. As fancy as that sounds, all the 3 things refer to the exact same thing. Let's take a look. Indices, powers, exponents. Those are the 3 words, right? All of them have a base, which is raised to a power, like you see so many examples over here. So you're supposed to have any base, a number, and to any power. Let's say 3 to 10. That I would then refer to as exponents or powers or indices. Now, what's given on the right-hand side, all these numbers are extremely important if you do recognize 2 square. What does that mean, by the way? 2 square. That means this number, which is in the base, is multiplied by itself 2 times. If, for example, I have 4 cubed, that would mean the number in the base, that's 4, is multiplied by itself 3 times. So over here on the right-hand side, we're going to be doing the square numbers. These numbers are from the times table, the 20 by 20 times table that we are trying to get into our system. But these numbers are so important, I thought we should go over them one more time. And because we're doing the topic powers, we will do 2 squared, 2 times 2, 4. Let's do this together. For 3 times 3, 9. 4 times 4, 16. 5 times 5, 25. 6 times 6, 36. 7 times 7, 49. 8 times 8, 64. These numbers are like gold for you when you're sitting for the GAT test because they come up a lot and they are somehow a bit more important than the timetables themselves. They are very golden kind of numbers. 9 times 9, 81. 10 times 10, 100. 11 times 11, 121, 12 times 12, 144, 13 times 13, 169, 14 times 14, 196. You see that they're like the reverse of each other. 169, 196. 15 times 15, 225. 16 times 16, 256. 17 times 17, 289. How much is 18 times 18? 324. 19 times 19 is 361. 20 times 20, 400. These these numbers are extremely important for you. Highlight them on the times table page, and you would be going over it over and over again. You'd be going through it over and over again in your times table 20 by 20. Next, we've got a few rules on exponents. Call it whatever you want. Exponents, powers, indices, they all refer to the exact same thing. Now, we've got a few rules on the exponents. For example, we've got when you multiply 2 exponents. Let's say, for example, I've got 3 to the power 5 is multiplying with 3 to the power 3. What you would do is, as long as the base is the same, so it's a 3, we add the powers. That gives me 3 to the power 8. Most of you might know this already. I'm sure all of you would know it already. But it's just so important to revise the basic concepts because GAT is not a test that's based on hi-fi information. It's based on the very basic information that we learned years ago. And likewise, if, for example, I have negative numbers, let's say I have negative numbers in the powers, the exact same thing happens as long as the base is the same. 3, what we do is we end up adding the powers. That's 3. 5 plus negative 5 is plus 2. So we add the powers. When 2 bases multiply, the same bases multiply, we end up adding the powers. What happens when we're subtracting them? For example, let's say 3, I'll take the exact same example. 3 to the power 5 divided by 3 to the power 3. As long as the base is the same, 3 and 3, we end up subtracting the powers, which is 3 to the power 2. Do you see how they are somehow similar to each other? They're somewhat similar. They're similar to each other, right? There's a thing behind it. We'll be discussing it over here in the notes itself. Next, likewise, I can have powers with negative numbers. I do the exact same thing because I'm dividing and both the bases are the same, 3 and 3. I end up subtracting the powers. So I have a minus 2 already. 5 minus minus 2, that would be 5 plus 2. That's a 7. 2, that's a 7. Now, so this is the case where we add powers. This is the case where we subtract powers. The next case is something where we multiply powers. When you've got a power on a power, so do you see that we haven't got 2 bases, it's just one thing. We've got a power on the power. What we end up doing is multiplying them. 2 times 3, that's 3 to the power 6. So when you have a power on a power, you end up multiplying. 2 special cases where we're looking at the powers of negative numbers. So far we've been doing positive numbers. What if I'm looking at the powers of negative numbers? Let's say I'll take negative 2. Negative 2, I'll put an even power on it. Negative 2, I'll put a 4 on it. Let's say negative 2 to the power 3, negative 2 to the power 5. What happens? Let's see. So that means, remember, the base is multiplying 2 times, so it's like negative 2 times negative 2. Now, exactly as we did multiplication of negative numbers, we did a while ago. That's 2 times 2, that's a 4. Negative becomes a positive. When I have it 3 times negative 2 times negative 2 times negative 2, that's 2, 2, 2, 8. 2 times 2, 4. 4 times 2, 8. What happens with the negative? The negative and negative, they cancel out. And I multiply with the third negative, so I have 3 negative. Minus, 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 so they cancel out. There's 1 left, so here I have a minus. Likewise, when I have it 4 times, I have 2 times 2 times 2 times 2. That's a 16. And I have a minus, 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 minus. 2 minuses cancel out with each other. The other 2 also cancel out with each other. So I'm left with a 16 only. When I have it 5 times, 2 times 2 times 2 times 2, 4, 4 times 2, 8, 8 times 2, 16, 16 times 2, 32. What happens with the negatives? 2 of them cancel out, 2 of them cancel out. There's 1 left over that I put here. Now, if you do pick a pattern, that would be when you have even powers, 2 and 4, you ended up getting a positive number. Although when you have odd powers, 3 and 5 are odd powers, you ended up getting negative numbers. So let's, for now, we'd remember, even powers, we get a positive. Odd powers, we end up getting a negative. So that's something that you'd like to remember. You can make a note of it on your worksheets if the information had gotten a bit rusty. Let's move on. Power is a negative number. So now, like we did earlier on, there was a power that was a negative number. And we took this example, 3 to the power 5 times 3 to the power negative 2. Actually, when you're looking at this thing over here, when the power is negative, the idea is if you flip it over, if the number changes from the numerator to the denominator, so you've got the numerator and the denominator, if it changes from the numerator to the denominator or from the denominator to the numerator, the sign of the power changes. Sign of the power changes. So for example, I have 3 to the power 5 times, if I flip it over, there's an invisible 1 over 1, right? So if I flip it over, it's 3 to the power, it's not negative 2 anymore, it's just a 2. That's the whole idea of having a negative in the power. That when you flip the sign of the base from numerator to denominator, from the denominator to numerator, the sign of the power changes. Because it was a negative in the numerator, it's going to be a positive in the denominator. And then it's just regular, I have 3 to the power 5, 1 over 3 to the power 2. If you do see, they're sort of being divided by each other, right? Or you could even think of it like this. I've got 3 5s in the numerator, and 2 of them in the denominator. So this cancels out with this cancels out with this. I'm left with a 3 cubed, 3 times 3, 9, 9 times 3, 27. So the idea of having a negative number in anywhere is, if, for example, I have 5 to the power negative 2 in the denominator, if I want to get rid of the negative, I would bring it to the numerator and make it to the power 2. The negative's gone. That's the idea of having negative numbers as powers. Then how about addition and subtraction? Let's see, I have 2 to the power 8 plus 2 to the power 5, or, okay, 2 to the power 5. Can I add them? No, I can't. What if I have 2 to the power 8 plus 3 to the power 8? Can I add them? No, I can't. The only special case where you can add powers is when you have the exact same thing of each other. Like you have 2 to the power 8 plus 2 to the power 8. Is that twice 2 to the power 8? So I'm saying an apple plus another apple is 2 apples. Likewise, it's 2 to the power 8 plus 2 to the power 8 is twice 2 to the power 8. Now I can simplify that a bit more because I know I've got an invisible 1 over there. So remember, when the bases are the same, we end up adding the powers. So that would be a special case where you can add, when you can perform addition. But anything where it's not the exact same of each other, it's whether the powers are different or the bases are different, I'm not allowed to work with them. Next, I've got another special case where I have 0 as a power and 0 as a base. Anything 100 to the power 0 would give me a 1. X to the power 0 would give me a 1. Anything to the power 0 gives me a 1. 0 to the power anything gives me a 0, because remember, this thing means the base 0 is multiplied 100 times. No matter how many times you multiply 0, you would still end up getting a 0. So 0 to the power anything is a 0. And anything to the power 0 is a 1. So those are the two things. Two more things that we would like to recall from what we learned in the previous years. And while we're here, I'll just say something else, like 1 to the power anything. 1 to the power 1,000 would still be a 1, because 1 times 1 times 1, 1,000 times is a 1. So that's that. Let's make use of all these things that we've recalled, and just try this example. If you're feeling quite confident about these concepts, give it a try without watching the workout, or else let's do it together. So I've got 3 square, and I've got 9 to the power 8. The only way in exponents, indices, powers in this topic, the only way you can work with any question at hand is if you've got the same base. You should have the same base, or you should have the same power. So only when one of the two things are equal, like are the same, that's the only time I can work with them. For example, over here, 2 and 8 are not the same, I can't work with that. 3 and 9. 3 and 9, that's 3 to the power 2, and I've got to change that 9 into 3 to the power something. I know 3 squared is 9, so I'll rewrite it as 3 squared to the power 8. So I rewrote this 9 as 3 square, and that power over there carries on, and everything over here has the power negative 2. Now that I have the exact same bases, well, actually, let's work on this thing first. It's 3 to the power 2 to the power 8. So it's a power on a power, which means I would end up multiplying them. That gives me a 3 to the power 16. 3 to the power 16. It's multiplying with 3 square. Multiplying with 3 square. When you've got the exact same bases, 3 and 3, you end up, what happens to the powers? You end up adding them. So it's 2 plus 16. 2 plus 16, which is a 2 to the power 3 to the power 18. And I had this negative 2, which I forgot about in the middle. Negative 2, negative 2, negative 2. So I have 3 to the power 18 to the power negative 2. What does negative 2 mean again? I want to get rid of it. So what I would do is just flip it over. So I have 3 to the power 18 to the power 2. Actually, I could also do the entire thing to the power 2, so which means the numerator and the denominator separately to the power 2. Actually, I think I forgot about explaining this. Let me go back and explain it to you in a minute. So I've got a power 2. How did I change it from negative to positive? I just flipped it over, and now I've got 1 square, which is a 1, over 3 to the power 18 times 2, because it's a power on a power. That's 3 to the power 36. Answer. There's one thing that we do need to recall. Where is it? Okay. So far, we've been looking at how to perform operations when the bases are the same, right? Now, what happens when, for example, the powers are the same? So if the powers are the same, that is the only case where I'm allowed to deal with the numbers, keeping the power on the side, which is otherwise not something that I'm allowed to do. Because the powers are the same, I'm allowed to put them on the side, deal with the numbers, 2 times 9, 18 to the power 100. Likewise, I've got the same powers over here, so I can put the 4 over 2 and put the power on the side, deal with the numbers first, 2 times 1, 2 times 2, and then place back the power. So to be able to work with any powers, question, indices, exponents questions, I should either have the same bases or the same powers. If I haven't, I'm supposed to make them the same. And when I've got something as a fraction, here, I've got something as a fraction, let's say 1 over 2, and the entire thing is being squared, that's the same thing as saying 1 square over 2 square, the fraction. If you've got a power on a fraction, the fraction of the square applies to everything within the fraction. Let's move on. To the practice, but before that, I'd like you to know something. These are values that come up a lot, which is why it's worth internalizing them. Just write them somewhere and go through them over and over again so that they register in. So that's 2 squared, 2 times 2. Actually, that's supposed to be 2 to the power 1, which is just 2. 2 squared, which is 2 times 2, 4. Let's do it together. So I've got 2 times 2 times 2. That's 2 cubed. 8. 2 to the power 4. 2 times 2 times 2 times 2. That's 16. 2 to the power 5. 2 times 2. Do you see that we're only multiplying by 2? Multiplying by 2, so I just multiplied by 2. 32, 64, 80, no, 128. 128 to 56. Likewise, you've got to retain a few powers of 3 as well. 3 to the power 1, 3. 3 squared, 9. 3 cubed, 37. 3 to the power 4, 81. That's 243. Just jot them down somewhere. You'll be going through them. So when the numbers come up, it's like, oh God, I've seen this before. That's all we need. 4 to the power 1, 4, 4 squared, 4 times 4, 16, 4 times 4, 16 times 64. That's 256. They're the same numbers here. 2 to the power 8 and 4 to the power 4 are the same numbers. 5 to the power 2 and 5 to the power, that's 5, 25, 125, 625. Maybe you know some of them already. 6 to the power 1, 6 times 6, 36. That's 216. Then we've got to the power 7, which is 749. And that was 343, or not. Yeah. Now, what I would like you to do is observe a pattern, because there's a pattern in here. 2, 4, 8, 6, 2, 4, 8, 6. Do you see the pattern? So whenever it's a power of 4, we've got a pattern 2, 4, 8, 6. The powers of 3 are 3, 9, 7, 1. Then again, you'd have 3, 9, 7, 1. So the pattern is 3, 9, 7, 3, 9, 7, 1. Powers of 4 are 4 and 6. 4, 6, 4, 6, 4, 6. So 4, 6. The powers of 5 always end in a 5, do you see? The powers of 5 always end in a 5. The powers of 6 always end up in a 6. The powers of 7, if you work them out, I'm not going to go through it, but if you work them out, the pattern is 7, 9, 3, 1. That's the pattern. And if you work out the pattern of 8, 8 has got a pattern and 9 has got a pattern. The reason we're looking into patterns is sometimes they give you a huge number, for example 5 to the power 20, and they're expecting you to get the answer, but here, if you know that it ends up in a 5, the power of 5 ends up in a 5, you can very easily, within 2 seconds, spot the answer and move on. Likewise, if they've got you a power of 4, let's say 4 to the power 19, now no way I know what that is, but what I do know is that odd number ends in a 4, even number ends in a 6, odd power ends in a 4, even power ends in a 6, so this is an odd power, it's supposed to end in a 4. That is the reason we're trying to observe the pattern, that these powers form. The pattern for the powers of 8, is 8, 4, 2, 6, and the pattern for the powers of 9 is 9, 1, 9, 1. So that's something you can make a note of in your worksheet. While we're at patterns, there is something with the square numbers as well, because once I came up with this very strange question, which we would do in the practice or in the revision somewhere, and they said something, like 2, 1, 6, 8, 8, and they said they had 4 options, and this was one of them, and it said which cannot be a perfect square. Which number from the 4 options cannot be a perfect square? And the answer was this one over here, because if you pay attention, no squares end up in an 8. Here, this is ending up in a 4, 9, 6, 5, 6, 9, 4. You would realize that nothing ends up in a 2, nothing ends up in a 3, nothing ends up in an 8. And not 7 as well. So square numbers never end up in 2, 3, 8, and 7. Square numbers never end up in a 2, 3, 8, 7. So weird questions like these can only be answered if you've noticed the patterns of these numbers, which is why, like I said, these numbers are golden. The square numbers and the numbers that we're doing over here, the powers, are very important. Just jot them down somewhere so you're often going over and over through them. Now, I know there are so many numbers that I'm asking you to internalize, but I assure you that this is one of those lessons where you've got so many things to internalize, but usually, like most of the lessons don't go by this. Even the upcoming lessons for algebra and geometry would not have this amount of information, because here you've done algebra geometry just a year or 2 years ago, so you'd remember most of it, which is why it's the arithmetics, which is the main thing, the big block, which is why I called it the blockbuster in the heading of this block. Okay, coming to the point that I find really exciting, the practicing the questions, because I find the explanation a bit boring, honestly. Although I do want you to be revising it, sometimes, most of the times for the GAT, because it's based on very simple concepts, the problem is not the question itself, the problem is that the basics are quite rusted, which is why I never ever underestimate the importance of going through the basics, the formulas, revising all of them. But anyhow, all said and done, this part is my favorite where I practice questions. I hope it's the same for you too. Let's start. Question number 1. We've got powers that are being divided by each other. Now, when I look at the x, g, and y, that can overwhelm you, because these letters, that's what they come in for, to get that puzzled up. So it's x to the power 6, g to the power 6, y to the power 6, over, divided by x to the power 5, g to the power 7, and y to the power 6. Now, what I would do is, remember, I'm only allowed to work with powers if I have the same base. I have the same base over here. I'll work with them together. So that's like saying, would I be right if I say that? Because it's 2 bases are being divided by each other, so I subtract the powers. That gives me x to the power 1. Then I work with the second base, which is g and g. That gives me a negative 1. Am I right? It's g to the power 6 minus 7. That gives me a negative 1. Now, I can write it as 1 over g, or it's the same thing as saying g to the power negative 1, because powers, when you flip them over, the negative sign goes away. So I'll just write g to the power negative 1, and then I work with this, y to the power 6 over y to the power 5. That gives me y to the power 6 take away 5, just a y. Now, where does it tally? Does not tally with this. It's exactly this one, because g over here is the same thing as g to the power negative 1. It's actually in the denominator. To the power 1, which is the exact same thing as option B. If you're finding these very, very comfortable and you're finding them very easy to solve, pause the video at every question, attempt it yourself, and then come back, take a look at the answer. Next question, quite similar, although they've tried to twist it up a little bit by changing the positions of the bases that are the same. So this is what I would deal with first. That's the same thing as 12 take away 10. That's 3 square. That here, too, the bases are the same, so it's 2 to the power 7 take away 5, which is 2 to the power 2. 3 square is a 9. 2 square is a 4. 9 times 4, 36. Easy peasy. Next question, I've got, well, how much is it? Very convenient. Anything, 1 to the power anything is 1 itself, and 6 to the power 1 means it's just a 6. That's a 7. Next question, we've got a power on a power, so it's 3 to the power 6 times 2, 12 over 3 to the power 4. When you're dividing, the powers subtract, and you get 3 to the power 8. I'm encouraging you again and again to pause the video and to mute them and try and be ahead of me so you get to see the answers while you're working. But try and be ahead of me or mute the video, attempt them on your own. Next question, 9, 3, 3. The minute I look at this question, I'm thinking, I've got to have the same basis. And what coincidence, they've got a 9 over here, which can be rewritten as 3 squared. So it's 3 squared to the power 12. That's the first part done. And I've got times 3 to the power 4. Everything is divided by 3 to the power 2. That's 2 times 12, 24, times 3 to the power 4 over 3 to the power 2. Very easy now because the base is the same everywhere. All I need to do is power plus power, take away power because it's in the denominator. I'm left with a 22. 22, 3 squared is 24. No, that's 28. Take away 2, 26. That's option B. Let's go, next question. Again, when I'm looking at this, no way can I find out the answer. I need to have the same power of the same base. But I've got a 3 here, and I know this comes to the powers of 3. 3 to the power 1, let's just do it like this. 3, 3 to the power 9, 3 to the power 3, 27, 81, 3, 43. So that's 1, 2, 3, 4, 5. That's in the powers that we're supposed to internalize in the beginning of this lesson. So I'd rewrite it as 3 to the power 4. Now that I've got the exact same base, I can work on the question. Because if the bases are the same, the powers have to be equal to each other. Because of the equals to sign, if it's 3 to the power something, should be 3 to the power something, should be the exact same thing. So what I do is, I'll just pick the powers, I'll ignore the bases altogether, I'll just pick the powers, and I'll say 2x plus 1 is equal to 5. And solve. So 2x, 1 goes to the other side. Operation changes, reverses, it becomes -1. That's a 4. Then I divide this side by 2, and I divide this side by 2. I'm left with just an x. So 2, x equals to 2. Next question. If you are struggling with the basic algebra, working with algebraic equations, we're going to be covering it in the next block, inshallah. Next question. This question is a bit weird because it doesn't click straight away what they are expecting. And one more thing that they do in the GAT is that when they write, for example, give us x, y, and your brain suddenly thinks, okay, I'll find x, and then I'll find y, and then I'll multiply them together and give it to them. But a lot of the times when they ask you about something together, like in this particular situation, you can't find them individually anyways, you have to find them together. Now when I'm looking at this question over here, I'm thinking they don't have the same powers, and no way can they be the same basis, because 5 and 6 have nothing to do with each other. I can't convert 5 into 6 to the power of something, I can't convert 6 into 5 to the power of something, unless I use the information that they've given me. So what they've given me over here are two things. What I'm going to do is take one of them and substitute it in the other, take one of them and substitute it in the other. Now I will be carrying forward with, let's say, this equation, this equation, and using this one to substitute over here. So what I would do is try and make everything 5. I know I've got a 6 over here. Can I replace it with 5 to the power x? Because they're saying 6 is the same thing as 5 to the power x. 6 is the same thing as 5 to the power x. So instead of this 6 here, I would replace it with 5 to the power x. The 6 is rewritten as 5 to the power x because the 6 is equal to 5 to the power x. And the y follows down, like it was, equals to 5. So I formed a brand new equation for myself where I have the exact same base on both the sides. So I have 5 to the power x. What's the relationship between them? Power and a power, they multiply, equals to 5. Now the bases are the same, I can ignore them. The only thing I'm working on is the power, because the powers should also be equal to each other. What do I have here? An invisible 1. Write 5 or 5 to the power 1, the exact same thing, which means I can say that the powers have to be equal to each other, so xy equals to 1. I hope that's clear. Next question is kind of simple. All they're saying is 7 to the power x is equal to 5, so then 49 to the power x equals to 1. Very clearly I'm observing that they just squared it. They had 7 to the power x, they squared it, and they got 7 to the power x. They squared it, and they got 7 to x, which is the same thing as 7 to the power 2, 49 to the power x. Now, if they squared the left part, the left side, they squared the left side, they have to square the right side as well. It's an equation. Whatever happened on the left-hand side has to happen on the right-hand side as well. So 5 has to be squared too. 5 squared is 25. That's your answer. So all they did is squared both sides. Next question, question number 9. I do recognize that I should have the powers the same or the bases the same. That's the only way I can work on any question at hand. Over here, very conveniently, they've given me 2 and 4. I know 4 is the same thing as 2 squared, so I can make all the bases the same. That 2 to the power 9, I just rewrite it as 2 to the power 9 over. That 4 over here, I would rewrite it as 2 square. And that 4 has a power of 5, which I would write here, plus, again, I've got a 4, I would rewrite it as 2 square, and then it has a power of 5 on it, over 2 to the power 9. Now, everything is a 2, 2 to the power something, so all the bases are in 2s, which means I can work on them. 2 times 5, 10, 2 to the power 10. 2 times 5, 2 to the power 10, over 2 to the power 9. What can I do over here? I would subtract it, so it's 2 to the power 9, take away 10, plus, this part here is 2 to the power 10, take away 9. So I'm left with a 2 to the power negative 1 from here, plus 2. 2 to the power negative 1 is the same thing as 1 over 2 to the power 1, which is 1 over 2, plus 2. Is that 2.5? That's 2.5, right? Which is option B. Done. Next question. We've got 20 questions over here. The first like up until 13, I think, are not too difficult, but then we would have a bit more challenging questions coming up, which is why, again, try and do them on your own. Try and do the questions on your own. Next question. First of all, I would rewrite it as 1 over negative 2 to the power 3, because I wanted to get rid of the negative here, which I did by flipping it over, changing the side of the fraction. That now is 1 over, okay, 2 times 2 times 2, 8, and the power is odd. Odd powers end up getting a positive or a negative. Odd powers end up getting us a negative. If it were an even power, it would give me a positive. What happened? Okay, sorry about that. Technical difficulties. So that's my answer. That's my answer. Part D. Next question, 11. Easy peasy, because I do know that odd powers end up getting me a negative, and then I only have to do x to the power 11, which will be the exact same thing as x to the power 11. So that's that. That's my answer. Next question. 12. Now again, I find this question a bit weird as well, but I have seen it a few times. They just go like a letter to a power of a number equals a number to the power of a letter. The only way possible that these two things are equal to each other when it's 11 to the power 11 is 11 to the power 11. So basically, the letter is the same thing as the power. The value of the letter is the same thing as the power, in which case value A is greater, which is 12, value b is an 11. You could have it come up as, let's say, b to the power 16 equals 16 to the power b, but now I do know that the only possibility for b is to be 16 itself. That's it. So let's go, next question. Question number 13. You've got value a, you've got value b. From the looks of it, which is greater? Usually because students see 100 over here, they go like value a is greater, but actually if you think about it, what's happening? 0.18 times 0.18 times 0.18 times 0.18. How many times? 100 times. And what's happening? Because they multiply together, and now that I do know the square numbers, I know that this is 324. I mean, I don't want to complicate the situation, but I'm just explaining, just for the matter of explaining. I know that 18 squares is 324, and I know I have 1, 2, 3, 4 decimal places, 1, 2, 3, 4 decimal places. Do you see how the decimal is going to keep moving onto the left, and you're going to be getting closer and closer to the 0 when you're multiplying it by 100. Whereas in this particular case, it's 1.8 to the power 10, so it's 1.8 times 1.8 times 1.8, 10 times, and 1 times 1 would give me something, but it's 1.8, so close to 2 times 2 is a 4, so it would actually be becoming greater and greater and greater. I know 18 times 18 is 324, and I've got 2 decimal spaces, 1, 2, so that's what I got. Like I said, we don't have to go into the square of 18. There's no need to work it out at all. As long as you can spot that the decimal is going to be moving backwards and backwards and backwards, and over here the decimal would move slightly forward. Actually, we have a whole number. When it squares, it would end up giving us a big number. So estimation is the best way to go through when you're doing questions like this one. Next question, I've got the base has 7, and then I've got powers. Looks quite easy. I can work with them because all the bases are the same. So 6 times 2, that's a 12. Take away this thing, divided by 7 to the power 9. But I'm a bit stuck now because I know that I can't perform addition subtraction on exponents. What do I do? In questions like these, I would highly recommend that I find it the easiest to just split the fraction, and so I would rewrite it as 7 to the power 12 over 7 to the power 9 minus 7 to the power 9 over 7 to the power 9. Because when you decide to add this up together, you get 7 to the power 9 in the denominator and in the numerator, right? If you plan to add this up, which is the same thing as this one here. So when you split it, that is the easiest way to work about questions like these. Now, this is 7 cubed because it's 7 to the power 12, take away 9, that's 7 cubed. Take away 7 to the power 9 over 7 to the power 9 is 1. 7 cubed, I know is 343 because we did it in the numbers just before in the beginning of the lesson, and take away 1 because anything divided by itself gives you a 1. Take away 1 gives you 342. By the way, when big questions come up like this, when big numbers come up, it could be quite overwhelming because big numbers are overwhelming, especially when you're sitting there without a calculator. But you've got to keep reminding yourself, they know I don't have a calculator. They are not expecting me to do long work. They are expecting me to be a bit smart with this because they are checking my attitude. So if you go by that thinking style, you would manage a lot better. Likewise, when you're dealing with powers, this is a fairly simpler question because it's quite straight away. When you're dealing with powers, decimals can come up again. That's the reason we did an entire hour on decimals. So the bases are the same. Oh, it's supposed to be multiplication. So the bases are the same, 17 and 17. And what happens to the powers? So what I'm supposed to be doing is 17 to the power 3.5 plus an x should give me 17 to the power 8. 3.5, now the bases are the same, just going to ignore them. What I would say 3.5 plus x should give me an 8. 3.5 and how much gives me an 8? Well, 3.5 and 4.5 gives me an 8. So this question just means to say out clearly that expect fractions, decimals, any kind of those things in the exponent questions as well. Okay, next we've got, again, looking quite an overwhelming question because there's so many letters and there are not enough numbers to work with. But the minute that I spot out, hey, they're doing something here, was a over b and now became b over a, which means they're dealing with the negative powers because a over b, if you flip it over to, let's say, b over a, what happens is you get the power negative 1, which is what they're using over here. So, and that makes everything very, very easy because I have a over b to the power x minus 1. I'll keep that. I'll flip over the second fraction to a over b. What happens? I end up getting a negative 1. But then I already have an x minus 3 as a power. So that's my question now. But it became so easy because I have nothing to do with the base. They are exactly the same as each other. So all I'm looking at are the powers. So which means x minus 1 should be the same thing as negative 1 times x, which is negative x. Negative 1 times negative 3, which is a 3. I'll place all the x's on the same side and the regular numbers on the other side. That's an x plus an x. When it's going to the other side, it becomes plus x. When negative 1 goes to the other side, the operation changes, becomes plus. So that's 2x is 4. X has to be a 2. Now look how easy that got, am I right? But the question did look very overwhelming in the beginning because of so many of these letters. So, next question. If something similar comes up, inshallah, you would manage to do it. Next question. But always, the trick to remembering, even if the exact same question comes up in the test, you might take it with a shock because as it is during the test, you are sort of under pressure. But the key is to keep reminding yourself, there's a trick to it. I have to use some of the basics that I've learned, and it's nothing too big. Then next, I've got 5 to the power something gives me a 3, 1, 2, 5. So it's a straightforward question on powers of 5, although that number looks a bit too big, but let me just recall the powers of 5. 5, 25, 125, 625. That's up until where we did it. So we haven't done the 3, 1, 2, 5, but do you see that it looks like it's going to be the next one? Because every time you're multiplying by a 5, right? So even in this case over here, you'd be multiplying with a 5. 6 times 5 gives me a 30 something. So definitely it's not going to be 300, it would be a 3,000 and something. So it's the next power. So I have 5 to the power 1, 2, 3, 4, 5. 5 to the power 5 is 3, 1, 2, 5. And then, now that I know 5 to the power 5 is 3, 1, 2, 5, they are interested in this piece of information here. I find out the value of a is 5, so I'd say 5 to the power 5, take away 3, 5 to the power 2 is 25. That's that. Next question. Now this question, initially it does look like, what do they want? It's like looks too demanding, but then suddenly I realize I've seen this number, I recognize it as 16 square. So that suited me down. And when I look at the power, this also, because I know 16 is 4 square. and it has something to do with it. And then 9 is 3 squared, and that has something to do with it. So all the numbers look a bit manageable now. Let me start working with them. The bases are the same. I can just, what am I supposed to do? Add the powers. 0.16 plus a 0.09. When I add them up, 16 and 9, I could just add up 16 and 9. That gives me a 25. In addition, we don't count all of them. We just count it once, because I have it like this. So it's 2 decimal places, 2 decimal places. The answer would also be only 2 decimal places. So 2 decimal places over here, and that's 256. Okay. Next, what I have is, by the way, I think I spotted it out when I was doing the powers, that 4 to the power something is also 256. What was that? 4 to the power 4? Makes sense, right? Because I can rewrite 16 as 4 square. I can rewrite 16 as 4 square, and then I can just follow on with the power. So 4 to the power 4 is also 256. You can pick any one of these. Either 16 square is this or this. We've covered both of them in this topic. So I would say 4 to the power 4, because I like smaller numbers. They make things look a lot easier. 0.25, I would change that into decimal, fraction. Here, like that. Now, I do note that 25 and 100 come up in the table at 5. That's 5 times 5. That's 5 times 20. Once again, that's 5 times 1. That's 5 times 4. So I have 4 to the power 4 times, I'm left with a 1 over 4. 4 times 4 is a 1. They cancel out with each other. So I have 4 to the power 1, which is just a 4. Who would have thought this question is going to be that easy? There is a bit of workout, but at the first glance, it looked like I could never ever solve it. But then it did make sense. Next question. So I've got a base, a power. What I would do first is change that into a fraction. That's 4 over 100. Then I do realize I have a negative power, which I'm not very interested in. I would change it, which means I would flip over the fraction, 100 over a 4, and I want to get rid of the negative. That's how we get rid of the negative, right? We change the places from numerator to denominator. So basically, I change the place of the 4 from the numerator to the denominator, and the place of the 100 from the denominator to the numerator, and thus I'm allowed to take off the negative. Again, this 1.5 is making me a bit uncomfortable. I would prefer to have it as a fraction, maybe. First, before that, let me just simplify that. 4 times 1, 4 times 20. 25. 4 times 1, 4 times 25. Yeah, 25. So I have 25 over here. That over here is a 3 over 2, or if not, we do the regular way of simplifying and changing to fractions. So that's 5 times 3, that's 5 times 2, right? So I have a 3 over 2 as the final power. And can I rewrite this as a 5 square? 25 is 5 square, right? So I end up getting 5 to the power 2 times 3 over 2. 2 and 2 cancel out. I'm left with 3 cubed. That's 5 times 5 times 5. 5 times 5, 25. 25 times 5, 125. Again, a number that we've done in the powers section already. Answer. Keep the number of powers. Well, we're only left with one question now, but you are allowed to keep the times table, the powers table in front of you to work with, because the idea is you go through them over and over again so the numbers absorb in. Question number 20. First of all, I've got like huge numbers, but thank God I do recognize that as a power of 3. Powers of 3, 3, 9, 27, 81, 243. 243. So 3 to the power 1, 2, 3, 4, 5. That's 3 to the power 5. I'd rewrite it as 3 to the power 5, and then it's multiplying with the power that's already there. 9 over 9. Beautiful. They cancel out. Times. I can do nothing to this over here. I'll just rewrite it. And then this can also be written as 3 to the power 2. And then there's a power, the n outside already, so I'll just copy it out. Very beautiful. Now I've only got powers of 3, which I would start to put together, because I have 3 to the power n, which is here, times means I would add the second power. So 2n plus 1. Then these are being divided. So I would have to subtract them, minus the first value, which is 2n, minus the second value. By the way, be careful with things like these, because when you're subtracting, it becomes negative n, minus negative 1. Minus becomes a positive 1. Do you see the signs changed? So be careful, because many times we just write it as, okay, negative n minus 1. No, that's not a minus, that's a positive, because the negative is applying to both n and the negative 1. So here, I've got 3 to the power, a long string of number, which I can work with, especially because n minus n, they're cancelling out. 2n minus 2n, they're cancelling out. 1 and 1 are adding on, so that's 1 and 1, 2. That's equal to 3 squares is 9. Oh my God. What a fancy way of writing 9. Ooh. Okay, now that we're done, I'm just reminding you to make sure that you do the table of 9 today, all the way from 9 times 1 to 9 times 20. Let's move on to the next section. Practice on analogies. So we've been learning about analogies past 2 days, and now we're going to be applying that all in as a reminder of what we were doing. So we try and make up a sentence that describes the relationship between the first 2 words, and then we use that for the third word, for the same relationship with the third word. So that's what we're going to be doing, practicing them. Let's start. Question number 1. They're saying odometer is to mileage as compass is to what? Now, odometer, even if you don't know what that means, that is that thing that has the needles on it and measures the mileage, is to mileage. Mileage, we understand what it is, right? As compass is to something. So odometer clearly looks like an instrument that is measuring the mileage. The compass is an instrument that also measures or tells us about something. What does it tell us about? About the speed? No. Hiking? No. Needle? Yes, it has a needle, but that's not the relationship we're looking at. We're looking at an instrument that is doing something. So the instrument is measuring a direction. The direction. To save time and to make things a bit clearer, what I've done is added a bit of description. So after every question, you would have its description in case the question itself did not register in, so I don't have to spend too much of time on each question. I'm going to question number 2. Marathon is to race as hibernation is to something. Now, marathon is this kind of race where you're running forever. It's like quite a few kilometers that you have to run. Usually people run in a group. So that means it's a long race. It's a long race. It's a duration of a very long length. So hibernation has to be something of a very long length. Hibernation happens in winter. Yes. Bears hibernate. Yes. In hibernate, maybe you're dreaming. In hibernation is sleeping. So hibernation is a long duration of sleep, which is why I would choose D. So remember to go through all the options slowly and carefully, because when I read winter, I realized, yeah, it does have something to do with hibernation, but it's not the relationship that we are looking for. Again, you feel free to go through the explanation, which is underneath every question, to understand it better if you haven't yet. Now, window is to pane. as book is to what? A book can be a novel. A book has nothing to do with glass, I think. A book has a cover and a book has pages. But what's the relationship we're looking at? A window is made of paint. A window is made of paint. A book is made of... Cover is the only outside of it, which is why we won't consider. It's actually made of the pages inside, so pages or page. 3. Next question, we've got cup is to coffee as bowl is to what? Very, very clearly, we drink in a cup. We drink coffee in a cup, right? So cup is used to drink coffee. Then bowl has something to do with dish, spoon, food, and everything looks like it's related to the bowl. But the relationship we're looking at is cup, you drink coffee in a cup. So what do you drink in a bowl? You can drink soup in a bowl. You can even have food in a bowl, but that wouldn't be as close to soup because you don't drink food in a bowl. You can have food in a bowl. Next, we've got yard is to inch. Now that's checking a bit of your, general knowledge, because an inch is quite small yet compared to a yard. Maybe we do know that already. Like people say, oh, I'll go out in the yard, which is their background yard. So yards is like a long thing, but inch is really small, just one block of your finger. As quart is to what? Now quart is, if you have seen, quart is this small box of milk or some kind of liquidy substance. Usually milk, they do have it, they sell it in a quart. So it's like a big thing to a small, that's measuring length, but this is measuring the volume of something that's liquid. Gallon, yes, that's liquid. Measurement, ounce, yes. Milk is liquid, but it's not measurement. Liquid, it's not measurement. So I have to choose from gallon and ounce. So it's something big to something small. So this has to be something big to something small. Gallon is huge compared to a quart. If that's a quart, this would be a gallon. Really big. So, but an ounce is quite small compared to a quart. So I'll go with the ounce. So questions like these might get a bit challenging. When you're sitting for the exam, stress, time stress, exam mark stress, etc., etc. It might not click. So this is what you want to be very careful about. Usually there are two answers that are very close to each other and two that are the opposite. So you're stuck between choosing between the two answers that are close to each other. Be careful about that. Next, we've got elated is to despondent, as enlightened is to. Clearly, they are the opposites of each other, so we're looking for an opposite of enlightened. When you're enlightened, you are aware. When you're enlightened, you are ignorant. No, that's the opposite. Oh, so that is because we're looking for the opposites, right? No, that's synonyms, so not. Enlightened, you're miserable. Not really. When you're enlightened, you're supposed to feel quite good. Tolerant has nothing to do with each other. This question over here had just one option. The rest of them did not make any sense, so we did not have any two numbers to choose from. Two options to choose from. Question number 7. Optimism is to cheerful, as pessimism is to. Now, when someone's an optimist, they always have a very cheerful outlook. No matter what horrible things are happening around, they're always quite cheerful. So that's a characteristics of an optimistic person. What's a characteristic of a pessimistic person? They're supposed to be something a bit sad, gloomy. Yes, makes sense. Mean, not necessarily. Pretty, no. Helpful, I don't think so. So gloomy. Again, easy question because I didn't have to choose from any two choices. Reptile is to lizard as flower is to something. Reptile is a big family and to it belongs the lizard. So flowers is supposed to be a big family to which belongs something. Petal, stem, daisy, alligator has nothing to do with it. A petal is a part of a flower. A stem is not a part of a flower. A daisy is a kind of a flower. So which one would I go for? Is a lizard a part of reptile? Not necessarily. I mean, reptile is like it's not something tangible. It's not something tangible, but lizard is a kind of reptile, I would say. Lizard is a kind of reptile. And daisy is a kind of flower. I'd go with C. Play is to actor as concert is to. Actors perform in a play. So who's performing in a concert? Actors perform in a play, so Dash performs in the concert. Maybe we can play pianos as well. We can. Musicians, but do you see that this is a person? So we've got to choose a person. Do you see how they're close to each other? Because this is a person. You would have musical instrument playing in the concert, but they're not talking about the instrument or part of a play. They're talking about the person who's acting. So musician performs in the concert. Next question. Sponge is to porous as rubber is to. Now porous is this thing where it's got like holes. So like water can pass through a sponge, right? That's what they mean by porous. So very clearly being porous is a characteristic of a sponge. What is the characteristic of a rubber? A rubber is massive, not necessarily. It's solid, yes it is solid. It's elastic, yes it is elastic. Inflexible, no it is quite flexible. So I'm having to choose between solid and elastic. Well, sponge is also a solid, but that's being more specific with porous. So being elastic is a more specific quality or characteristic of a rubber. Next we'll be practicing a lot more questions tomorrow because indices was a big topic. I only opted to do 10 questions. Tomorrow with square roots we'll be doing a lot more questions. I would like to remind you to add the 5 new words into your workout journal. Pick anything from here. That's if you did not understand anything. If any word was new to you, pick that from there. Remember, we're looking for very basic words, nothing too fancy. And I'll catch you tomorrow. Till there, keep practicing, keep shining. I'll catch you tomorrow. Take care.